So today we are going to have lecture 8. So let me first recall the things that we have already done. We had learned about how to do algebra on matrices, adding matrices, subtracting matrices. But the main thing that we had focused last time was to take the product of two matrices. And we had learned a bunch of ways of doing it. One of them was taking the ith row of matrix A and taking its dot product with the jth column of matrix B. Then we had also said that this thing could also be thought of as linear combination of columns of A. So linear combination of columns of A. And the matrix product can also be thought of as linear combination of rows of B. Okay. So we had seen examples of all these things, and as we go along, we will see how to keep on using this and which form is more advantageous in certain regards compared to the others. Now, one thing I would like to remind you about the matrix multiplication is a very special thing. And we have to keep in mind that there are certain restrictions under which this matrix can be, two matrices can be multiplied. So first restriction was that if I have a matrix A of size m by n and a matrix B of size n by p, the number of columns of A must match the number of rows of B. For the matrix multiplication A times B to be defined. So if this condition holds true, then the resulting matrix would be of size m by p, m rows and p columns. And in which case we can talk about the product of the two matrices. Now the moment we see this thing comes to us immediately, that B times A need not be even defined So the thing is, this is first kind of non-intuitive thing that we see for the first time, that A times B need not be equal to B times A. So the matrix multiplication is not commutative. Now this is the first time perhaps many people see things with an operation where things are not commutative, even though you would have seen division, which is also not a commutative operation. But this is another instance where you see matrix multiplication is not commutative. And in fact, one can ask a question, well, under what circumstances AB will not be equal to BA? For example, in this case, we are saying A times B is defined because of the sizes of the A's and B, and B times A need not be even defined. So for example, when we have A as a 3 by 4 matrix and B as a 4 by 5 matrix, we know that AB would be of size 3 by 5, but B times A is not defined. So one can ask a question, could it be possible that when both AB and BA are defined, at least in terms of sizes, in that scenario can AB be equal to BA? So let's see, what if A was of size 3 by 2 and B is of size 2 by 3? In this case, both AB and BA are defined. AB will be of size 3 by 3 and B times A would be of size 2 by 2. So both of them are defined, but as you can see, because of the difference in the size, AB will not be equal to B times A. So in some sense, commutativity is not lost just because B times A is not defined. Even if B times A is defined, it could still happen that the two matrices are not the same. So then one may ask a question, what if both matrices AB and BA are of the same size? Can it be true that A times B will always be equal to B times A? So let's try a scenario. Say A is of size 2 by 2, B is also size 2 by 2, then both AB and BA are of size 2 by 2. So at least this time there is no disparity in the sizes. Can it still happen that A times B need not be the same as B times A? You will see pretty much if you pick any random matrix, unless you just happen to be picking so-called a diagonal matrix and stuff like that, you can check A times B will not be equal to B times A. So the chances of you picking two matrices which commute will be fairly low. And the best way to see that this thing is not equal to that other product is if you just perform the matrix multiplication. Out here the first entry would be 2, and in here the first entry would be 21. So definitely these two matrices are not equal to each other. So it's not because of the size incompatibility, it's not because of the lack of being defined, it's just that matrix multiplication will lose out on commutativity because of the way things are defined. In fact, the inspiration behind matrix multiplication is that of function composition. And as you very well know, function composition is not commutative, and pretty much the same thing is happening in matrices also. Okay. Now let us look into other kind of surprising scenarios which happen in matrix multiplication. Things which we are kind of used to, but may no longer be true in matrix multiplication. So let us see what those things are. These are some results which we kind of take for granted when we are dealing with numbers, but they may no longer be true in matrices, and we have to be careful about them. So let's try. One of the things which we kind of take for granted is things like this. What would be A plus B whole square? We kind of have a habit of writing it as A square plus 2AB plus B square. But let us see how it will look like in terms of matrix multiplication. So A plus B times A plus B. So if we perform the matrix multiplication, we are assuming that A and B are of nice size so that all these multiplications can be performed. So without loss of generality, let us assume that A and B are both square matrices, so that we don't have to worry about whether some multiplication is defined or not. So something like this plus B times B. Now, matrix multiplication is distributive, so using that idea, we can get something like this. This is what we call as A square. But out here, we have to be careful. We simply cannot say that this thing is 2 times BA. This need not be 2 times A times B or 2 times B times A. Because A times B need not be equal to B times A. So in general, you cannot say anything except that, oh, it will be AB plus BA. This is one of the things which we kind of love to do, but you have to be careful. You cannot simply write this as twice AB. Likewise, we have seen that we have a habit of writing things like this: a minus b times a plus b. These kind of things need not hold for matrices. So we have to be careful about these kind of identities. We will be tempted to use them many times, but we have to make sure whether they will hold true or not. Another thing that is, in my opinion, even more surprising, at least when you see it for the first time, or at least it kind of tells you that you have to be even more careful. What if the product of two matrices is 0? Does AB equal to 0 imply that A is 0 or B is 0? See, this is the property that we use in real numbers or integers. That product of two things is 0 implies one of them is 0. It's a very fundamental property of things like real numbers, complex numbers, integers, because they are all what we call as an integral domain. But is it true for matrices? So let's take a simple example. So here is my matrix A, which is 1, 0, 0, 0, and here is my matrix B, let's say 0, 2, 0, 0. If you take the product of these two matrices using any method that we have seen, then you will get, we have to change one entry. Let's see. If we multiply these two matrices, 1, 0 times 0, 0 gives you 0, 1, 0 times 0, 2 gives you 0, and you have 0. Okay, so A times B is 0, whereas neither A nor B is 0. So two non-zero matrices can combine to give you a 0 matrix. So we cannot say for sure that this is true. This is not a 0 matrix, this is not a 0 matrix, and yet we have a product as 0 matrix. So keep in mind these kind of anomalies that are there, and that should prevent you from just taking this for granted. So let us see how this matrix multiplication helps us in doing what we want to do. See, one of the reasons we are interested in matrix multiplication is that not only it gives me way to do algebra on matrices, it also helps use matrices for many purposes. So one of the things we want to take care of is, let me get this out of our way so that so imagine up until now we have been looking at the system of equations. We used to create an augmented matrix out of it, which was something like this. We used to do row operations to talk about the solutions of this system. But with this newfound knowledge of matrix multiplication, we can also write this as, look at the coefficient matrix that we have here. This is my coefficient matrix. So this is 1, 3, 2, minus 3. I can rewrite this system of equation as my coefficient matrix times the vector xy is equal to the right hand side vector 5, 7. So from now on, we can have the luxury of converting a system of equation using matrix multiplication. We can convert it into this form, AX equal to B. The reason this form is so convenient for us is because it reminds us of the way we deal with the equation. So if, for example, we all grew up with looking at equations like this, 3x is equal to 2. It kind of reminds us you of that. And how do you solve this? Well, you say, oh, I'm going to multiply by the inverse of 3 on both the sides, which is 1/3. And this is how you solve. So we are hoping that maybe something like this can be done for matrices. Somehow we can talk about inverse of a matrix and try to get the vector x using the idea of inverses. Can it be done? Or how will it be done? These are questions we are going to answer in the future. But this is the reason why we are so fond of matrix multiplication, because it kind of helps us think of system of equations exactly like the way we are used to. Okay, now before we exploit matrix multiplication, there are a few things which I want to make sure we understand. It's about some special kind of matrices. Since we are going to use those kind of matrices every now and then, so it's a good idea to at least be aware of their definitions. Okay. Now, all the definitions that I'm going to discuss now would be for square matrices. So all these special things that we have, or special matrices, are all square matrices. So we can think of them as n by n matrices. So the first matrix that we want to talk about is the so-called diagonal matrix. So what is a diagonal matrix? Well, as the name suggests, it's a square matrix which has entries only on the diagonal. So that means we will have things like some bunch of entries on the diagonals. Everything off the diagonal is just a zero matrix. Okay. So what we are saying is all the entries Aij are zero if I is not equal to j. Notice we are not saying anything about the entries when I is equal to j. That means those entries could be zero, they could not be zero. But all we care about is things above the diagonal and things below the diagonal should be zero. Any such matrix we will call it as a diagonal matrix. Okay. Then there is an upper triangular matrix. As the name suggests, the shape of this matrix would be, so imagine if you have a square matrix, you can split it into two halves along the main diagonal. So if we have a matrix where the lower half is all zero and the upper half could have zero or non-zero entries, then we will say we have an upper triangular matrix. So in terms of this, we can say all the entries which are in the lower half of the matrix are zero. So when you want to describe the lower half, you will say Aij is zero whenever I is bigger than j. If that is true, then we say that we have a upper triangular matrix. Likewise, we have the lower triangular matrix. Where, as you can guess, we are saying that the lower end of the matrix could be anything, but the upper end of the matrix above the diagonal should all be zero. So in this case, we will say that Aij is 0 whenever I is less than j. So these are some special matrices. They will have their own usefulness as we go along. There's one more matrix that we would like to talk about. This is the so-called identity matrix. This matrix has very nice property. We generally refer it to as I sub n, and it has ones along the main diagonal and 0 everywhere else. So it's a diagonal matrix with ones as the diagonal entries. And the beauty of this matrix is, if I have any n by n matrix and I multiply it by this identity matrix, it will give back my matrix A. So in a manner of speaking, the matrix In, or the identity matrix, acts like 1. It's the same kind of thing that 1 does in real numbers. You multiply 1 by any number, you'll get back the same number. So in general, in mathematics, whenever we see such a notion, you multiply by this special object, any object of your set, and if you get back your object, then that special object is acting like the multiplicative identity. Okay. Let me try it again and see if it makes some difference. Okay. Okay. So let's see. What else do we want to know about special matrices? Oh, yeah, there is one more special matrix, which is a useful guy. Remember, all these are definitions for square matrices, so the concept of diagonal, upper triangular, lower triangular, we are confining them to square matrices. So another one which we are interested in is the so-called permutation matrix. So the permutation matrix is basically a matrix obtained by permuting the rows of the identity matrix. So for example, if you look at a 3 by 3 identity matrix, and suppose I permute its rows, say something like this. This is our example of a permutation matrix, because this has been my fault. This is an example of a permutation matrix because we have obtained this matrix by permuting the rows of identity matrix. Now, why are we so fond of this matrix? You will see permutation matrix exactly does what the name suggests. It permutes things. So for example, look at what will happen if I take x, y, z and multiply it using a permutation matrix. Upon matrix multiplication, this is what I'm going to get, z, x, y. So the effect of a permutation matrix on a vector is basically permuting that vector according to what the permutation was for your permutation matrix. This is the thing which will help us in row swapping. So this is the matrix which is helpful for row swaps. Now that we have seen a few of the special matrices, let's try to see what else is there which can be kind of useful for us. Okay. In fact, if you look at all possible permutation matrices of size 3, suppose I create a set of all matrices of size 3 such that A is a permutation matrix. You can see that this set is closed under multiplication. What it means is if I take a matrix A and I take a matrix B, both of them are permutation matrices, then the product of those two permutation matrices will still be a permutation matrix. So in fact, if any of you knows things in group theory, this is basically saying that the set of permutation matrices is forming a group under matrix multiplication. By the way, in this particular case, let me call this as S3 so that I'm reminded that it's a 3 by 3 matrix. If you think about it, the number of elements in this matrix, this set would be 3 factorial, because you have 3 rows to permute and you can do them in 3 factorial ways. So this set will have size 6. So those of us who may know group theory can think of it as a group of size 6. Okay. Anyways, this is a little bit of a digression, but let's see what else we are after. Can you change this without any problems? The marker in here. Okay. Now, let me introduce an operation on matrices, which is kind of very unique to matrices. You don't see it in other contexts, but it's kind of a useful thing to know what matrices. And this operation is that of a transpose. The notation we have for this is A with us exponent kind of of t. It's not actually an exponent, it's just a symbol as a superscript, you can say. So suppose I have a matrix A which is of size m by n. Notice we are no longer confining ourselves to square matrices. So if I have A which is of size m by n, then we define the transpose of A as a matrix of size n by m. So basically the rows of A become the columns of A transpose. So this is how we obtain A transpose and vice versa. So for example, if I have a matrix A, which say looks like 1, 2, 3, 4, 5, 6, then the transpose of A would be the matrix where rows of A will become the column of A transpose. So 1, 2, 3, 4, 5, 6. So as you can see, we started with a 2 by 3 matrix, and A transpose happens to be a 3 by 2 matrix. Okay. Now one may wonder, why are we so fond of just flipping it? The thing is, transpose operation has quite usefulness for us, which will not be evident for some time. So let's at least just play with the transpose operation and see what all things it can do for us. So there are some properties of the transpose which are easy to verify, which I leave it for you as an exercise. So one of the properties of the transpose is, if you take the sum of two matrices and its transpose, it is basically the sum of the transposes. If you take a scalar multiple of a matrix and its transpose, then the scalar multiple, as expected, will not change, and it will be k times A transpose. Perhaps the most useful of the properties of transposes is this one, which will take a slight bit more effort to prove. Which is AB transpose is basically B transpose, A transpose. Notice how the order has changed. And if you think a little bit, it will be kind of intuitively clear why this order should change. So for example, if A was a m by n matrix, B was a n by p matrix, in that case, A transpose must be a n by m matrix, and B transpose must be a p by n matrix. So you can pretty much guess from the sizes of the A and the B transposes that the only multiplication that could possibly be defined in a general scenario would be B transpose times A transpose, because then only these two guys are going to match. So in some sense, it's an intuitive way to guess the validity of the formula. But the last this property is something which I highly recommend you to try to write a proof. It's not a very difficult proof, but at the same time not a very easy one also, and it gives you a good practice in writing a general proof regarding matrix multiplication. Okay. Okay. So let us see some nice things about transpose, some of the properties it can help us with. So one of the things transpose helps us in is defining properties about matrices. There are two types of matrices, symmetric matrices and skew symmetric. So we say a matrix is symmetric if that matrix is the same as its transpose. That means the operation of transpose does not change the matrix. If that happens, then it's a symmetric matrix. And we have another type called the skew symmetric matrix. So we will say A is skew symmetric if A transpose happens to be minus of. Notice just by the definition itself, it is quite evident that the idea of a symmetric or a skew symmetric matrix can only be implemented on a square matrix, because you want the thing to be a multiple of its transpose. So the sizes of that A transpose and A must be the same, which can only happen for a square matrix. So here is something worth noticing. Consider this matrix A times A plus A transpose. Okay, suppose I have a matrix A, which is a square matrix. So A transpose must also be a square matrix, the same size. So that means we can talk about A plus A transpose. And we call this matrix as B. Is B symmetric? Suppose I want to test whether B will be symmetric or not. You see, to test symmetry, all I need to do is talk about what is B transpose. Well, since B is A plus A transpose, so B transpose would be the transpose of this. Then by using property number 1, the transpose of this would be A transpose plus A transpose transpose. Now, question is, what would be A transpose transpose? You think about it in the definition of A transpose. A transpose will flip the rows to columns, but taking another transpose will flip it back to rows. So rows becomes column, then column become back to rows. So that means A transpose transpose must be A itself. So this is another property that we could have added to our list, that the transpose of a transpose give you back A. So in some sense, transpose is an operation which applied twice brings you back to A. These kind of operations have a name. They're usually called the idempotent operations. But don't worry about the name, they're not going to really help you or hurt you here. A transpose plus A is same as B. So since B transpose turns out to be equal to B, therefore we can say B is symmetric. So if you take any matrix A, add to its transpose, then the sum matrix will always be a symmetric matrix. Okay. Let's try with one more thing. Let's consider another matrix, C, which is of the form A minus A transpose. Is C symmetric? Or skew symmetric? So let's try it again and see what happens to C transpose. C transpose will be A minus A transpose, whole transpose. Transpose can be distributed in a manner of speaking by one of the properties we saw. So this becomes A transpose minus A. Now look at this. The relationship between A transpose minus A and A minus A transpose would be simply by multiplying it by the scalar minus 1. So now we have C transpose as minus C. Therefore, we can say that C is skew symmetric. So at this stage, one may wonder, if I am given a matrix in general, is it always the case that either it will be symmetric or skew symmetric? Or could there be matrices which are neither symmetric nor skew symmetric? So let's try to answer that and see where does that take us. For example, let's take a look at this matrix, 1, 2, 3, 4. Suppose this is A, and A transpose would be of the same size, 1, 2, 3, 4. As you can see, A transpose is neither equal to A nor it is equal to minus A. Therefore, neither this matrix is symmetric nor it is skew symmetric. So in fact, being a symmetric matrix or being a skew symmetric matrix is kind of a special thing for a matrix. And once it has that property, then it can help us understand its behavior a bit better. Let's make one more quick observation. Suppose I look at a 2 by 2 matrix. Let me call it as ABCD. I want to know, do the entries have to be something special for this to be a skew symmetric matrix? So that means if I look at A transpose, this will be A, B, C, D. If I want anti-symmetry, skew symmetry, for skew symmetric, I want A transpose to be equal to minus A, which means that the matrix that I have written for my A transpose must be equal to the matrix I get by multiplying each of these guys by a minus. Now, remember, these two matrices must be the same, so A must be the same as minus A, D must be the same as minus D, which can only happen when A and D are 0. So what does this tell us? This tells us that for a skew matrix, the diagonal entries must be 0. Even though I have showed you only on a 2 by 2 case, but for a general case, the same idea will work, and you can try to generalize it for any n by n matrix. So here is a result which we can keep for us. It's again a result which will help us in future. If A is a skew symmetric matrix, then the diagonal entries have to be 0. Okay. Okay. I should kind of caution at this stage about one thing, not that it will affect to most of us at this stage or at this level, but this result that I have written is true pretty much for almost every kind of situation, except when you are working in very special field. For example, if you're working in field mod 2, then A could be equal to minus A without A being 0. So having said that, I know that statement may not make much sense for many of us, but these kind of things you should always keep in mind that they are being done in very special fields, like real numbers and all, where life is quite comfortable and not very surprising. Anyways, this is something that will have some impact later on. Here's a question for us. If you recall, given any function, f of x, you can always write it as a sum of an even function plus an odd function. Suppose my function is defined over all real line, then I can always write it as an even function plus an odd function. This is something that sometimes you see in calculus. We ask the same question over here. Given any matrix A, of course we are talking about a square matrix A, is it possible for us to write it as the sum of a symmetric matrix plus a skew-symmetric matrix? Can every A be written as a symmetric matrix and a skew-symmetric matrix? The answer turns out to be kind of surprisingly simple. The idea, these two things are actually very, very similar to each other in construction. And that is the beauty of the math behind it. So if I have a matrix A, a square matrix, I want to write it as the sum of a symmetric matrix, let me call that to be B, and a skew-symmetric matrix, let me call that to be C. So I want B to be symmetric and I want C to be skew-symmetric. So let's see what is A transpose. A transpose would be B transpose plus C transpose. But didn't we say that B is symmetric? So B transpose must be B. And C transpose would be minus C because C is antisymmetric. Now I can solve for B and C. If I add these two matrix equations, I will get B must be A plus A transpose over 2. And if I subtract these two guys, I will get C as A minus A transpose over 2. And if you remember, just a while ago we have already shown that A plus A transpose is a symmetric matrix, A minus A transpose is a skew-symmetric matrix. So we can always write any matrix as a sum of a symmetric plus a skew-symmetric matrix. So one may question, what's the advantage of doing it? Well, one thing is it's fascinating. Another thing is, since every matrix can be broken into a symmetric and a skew-symmetric matrix, that means if we have some idea about how symmetric matrices behave, perhaps that can help us understand how my matrix will behave. So we'll continue from here in the next session.